Hi, this is Nastyanowski. Class is Discrete Structures. We're up to section 2.1, an informal introduction to elementary logic. Okay, so let's put everything in context. We spent the past month talking, or five classes, talking about sets and how they relate. Now we have a totally new topic, and this is what I told you in the beginning of the class. This course is just a lot of different topics. This topic is a lot of fun. It's about logic, and it's going to be used all over. Okay, and so now you might have seen some of this in high school, you might have seen it in elementary school, some of it will be totally obvious. We talk about and or and stuff like that, but we have to do it, and we have to do it carefully, and you got to see it again so that you get it into your head. Okay, so what's logic about? Hold on. Okay, so sets, what we dealt before with was sets. Logic is all about propositions. What's a proposition? So let's make a definition. Definition, a proposition, okay, is a sentence. Okay, so we're defining the word proposition that is either true or false. It's one or the other. It's either true or false. Logic deals with this true or false, 1, 0. Computers deal with 1, 0, true or false. So this is going to be central to all of that. Okay? So things are either true or false. Now, let me give you some examples of things that are propositions, and I'm going to give you examples of things that are not propositions. You ready? Julius Caesar was president of the United States. That's a totally legitimate sentence. It is a proposition. It happens to be a false proposition. Julius Caesar lived in Rome or something like that. He was never a president of the United States. Let me give you another example. 2 plus 2 is equal to 4. That is a proposition. It happens to be a true proposition. Some propositions are going to be true, some are going to be false. Okay, here's one that we saw before. If a set has n elements, then it has 2 to the n subsets. We talked about this when we talked about power sets. Now that is a statement it's true. It happens to be true. Okay? But it's written in an if-then statement. We're going to have some propositions are like that. Okay, let me give you another proposition. 2 plus 2 is equal to 5. Okay, that's perfectly legitimate. It happens to be false, but it's perfectly legitimate. Okay, it's a proposition. Let me give you a more interesting one. Okay, and we're gonna argue about this. Okay, it is not true that 3 is an even number, or 7 is a prime number. Okay, so let's go through it. First of all, is 3 an even number? No. Okay, is 7 a prime number? Yes. Okay, so now let's see if this is true. It is not true that 3 is an even number. That happens to be, it's not true. Or 7 is a prime number. Now there's two ways of reading this. I'm going to write it like this. Okay? You can read it like this. It is not true that 3 is an even number. It happens to be true. 3 is an odd number, so this is true. Or 7 is a prime number. Okay? That's true. So this is going to be true or true. Okay? But that's one way of reading it. Okay? What's another way of reading it? Okay? You can read it like this. Okay? It is not true that 3 is an even number or 7 is a prime number. Okay? Okay. 3 is an even number, that is false. 7 is a prime number, that is true. Okay? But is it not true that these things are true? Anyways, this or this is true. So it's a little ambiguous. It's not, we're not sure what it means. Let me give you another example of a sentence that is ambiguous. Jack is tall. I don't know. Whose definition of tall? Taller than me? Taller than you? Okay, that's a vague statement, so we don't know if it's true or false. It's cold outside. Well, it might be cold to me, but it might not be cold to you. So those are vague statements. Vague statements are not propositions. Propositions are statements that are either true or false. Okay, let me give you some other examples of sentences that are not propositions. You ready? What's for supper? Okay, what's for supper? That's a question. Questions are not true or false. Questions just are. They're just questions. Okay, your place or mine? Would you like to go to your place or would you like to go to my place? Again, that's a question. Questions are not propositions. They're not true or false. Okay, next, clean your room. That is not a proposition. That's a command. I'm telling you, do something. Okay, okay. And no one listens to me in this house. My kids are here. Okay, so they don't listen to me, but that's fine. So it's not a false command. It just doesn't work. It's a command that doesn't work. Okay, but what is logic interested? It's not interested in commands. It's interested in propositions. Go directly to jail. That is from the game of Monopoly, but it's a command. It's not a thing. So usually sentences can be split into one of three things. It's either a proposition, a statement, which is either true or false. The grass is green, the refrigerator is white, I am smiling, my kids are beautiful, etc., etc. Those are true propositions. Then there'll be false propositions. Then you have questions and commands. We're not going to be interested in questions and commands. We're only interested in propositions. Let me give you another statement that's not a proposition. Seems like a proposition. X minus y is not equal to y minus x. That seems to be true, except what happens if I plug in 5 for x and 5 for y? 5 minus 5 is equal to 5 minus 5. Okay? Yes. 5 minus 3 is not the same thing as 3 minus 5. I agree. But sometimes x minus y is equal to y minus x. So that's an ambiguous statement. We don't know what it's stating, what it's not stating. Also, we're going to have this. A times b is equal to b times a. Now, for numbers, that's true. 5 times 3 is equal to 3 times 5. But a and b might be matrices or something else. Okay, and so those aren't very clear. So these are seemingly math statements, but they happen to be ambiguous. You have to put in all the information you need. Great. Okay. Okay, so now we know what logic is talking about. Logic, again, sets, we're all about sets, and logic is all about propositions. But now we have something else. Okay? And the idea is operations. So, let's just review. When we were talking about numbers, basic arithmetic, we had basic operations. Take two numbers, you can add them, you can multiply them, you can subtract them, you can divide them, okay? You can do exponential. All those things are operations of numbers. You take one number, you take another number, you do an operation, you get a third number. 5 plus 3 is equal to 8. 5 times 3 is equal to 15. 5 minus 3 is equal to 2. 5 divided by 3 is 5 over 3. Okay, each one is an operation. You take one, you take another, you do the operation, you get something out. So too, we're going to have such operations in logic. Okay, I'm going to have different operations in logic. So let me just go through quickly 6 operations that we're going to see. Okay, and we're going to go through them very carefully. This is the not operation. And again, these operations, you take a proposition, sometimes you take a second proposition, you do the operation, you get out a third. So let me just give you the operations first. And, or, okay, implies, this is sometimes called if and only if, or by implication. That's a little bit more complicated. Okay, and this is exclusive or. Okay, so those are 6 operations. We're going to see some other operations also, but let's talk about these operations. Okay, so again, what do these things do? They take propositions. Okay, they take propositions and then they do things with them, and then they get another things. So the and and the or I assume you've seen. So let's just go through them very quickly. Okay, if P is the proposition, it is raining outside. Okay, then not P. So P is a proposition. Not P is it is not raining outside. Okay, if Q is I did my homework, not Q is I did not do my homework. Okay, great. So here's some nice examples. Okay, so not just negates what it says. Okay, today is Tuesday, today is not Tuesday. Whatever proposition you have, you can negate it. Great. Now let's do some others. P and Q, that's a new statement. So P is a statement, Q is a statement. P and Q is a new statement. Just like one number and plus another number, you get a new number. Okay? P and Q stands for, in this case, it is raining outside, and I did my homework. Okay? So here's one statement, and it is, again, either true or false. Let's go through it. When is it true? Well, if it's actually raining outside and I did my homework, then this statement is true. If it's raining outside and I didn't do my homework, then the statement, it is raining and I did my homework, is not true. Okay? Because it has to have both of them as true. Make sense? Okay, great. Let's do P or Q. This stands for it is raining outside, or I did my homework. Okay, one or the other, or both. Okay, we can have one or the other or both. Okay, great. So here's more examples. Great, so this, we did not, we did and, we did or. The more interesting one is the implies. Okay, so this you might not have seen in high school, so let's do this. Okay. P arrow Q, and this is the one that students find the hardest. P arrow Q stands for if it is raining outside, then I did my homework. Okay? Now, that might be true, might not be true. Usually, whether it's raining outside or not has nothing to do with your homework. But we're making a statement here. And we want to know, does this statement imply this statement? If it is raining outside, then I did my homework, yes or no? Okay? We're going to have a lot of examples of this. And let me give you some others. Okay? So here's another one. P stands for driving faster than 60 miles per hour. Okay? Q stands for getting a ticket. Okay? And the idea is as follows. P arrow Q says if you drive faster than 60 miles per hour, then you will get a ticket. Okay. So this arrow is very important, especially in computer science. Okay, you're always going to have, if the user presses this button and this is in this variable, then we do this. If this is this and this is that, then we do that, etc., etc. So there's always a lot of arrows, there's always an implication, and we're always going to find them out. Okay. I want to write them. The book goes crazy about all the ways you can write this arrow. Again, it's complicated, so let's do it. So we can write it as follows. Hold on, let's do it. Let's write this arrow and say it in English in 5 different ways. P arrow Q. P implies Q. Okay? That means if one thing is done, then we do the other one. Again, we're gonna see some other examples of this thing, but let's do this. Next, you can also say it like this. If P, then Q. Okay? And sometimes I say P arrow Q. Okay? But let me give it to you 2 others. You can also say the same thing. Q whenever P. Let's do this like this. You will get a ticket whenever you go more than 50 miles an hour. Okay? If you don't clean up your room, I will be angry with you. My son and daughter are here. Okay? So that, what is that? I'm sorry. I will be angry with you whenever you do not clean up your room. Okay? So another way of saying that is, if you don't clean up your room, I will get angry at you. If you don't clean up your room, that implies I will get angry at you. If you don't clean up your room, then I will get angry at you. If you don't clean up your room, arrow, I will get angry at you. If you don't I will get angry at you whenever you don't clean up your room. Okay, one more. Okay. I will get angry at you if you don't clean up your room. Okay, so that's 1, 2, 3, 4, 5, 6 ways of saying it. Okay, let's do it in terms of if you drive. If you drive faster than 60 miles an hour, you will get a ticket. Driving faster than 60 miles an hour implies you'll get a ticket. If you drive more than 50 miles an hour, then you will get a ticket. If driving more than 60 miles an hour, arrow gets a ticket. You will get a ticket whenever you drive more than 60 miles an hour. You will get a ticket if you drive more than 60 miles an hour. Okay, let's do another one. P stands for raining. It's raining. And Q stands for clouds in the sky. Okay? So, question, where does rain come from? Rain comes from the clouds, right? So, if it's raining, then there are clouds in the sky. By definition, if you see water coming down your window, and unless there's a joker upstairs who's pouring water from his window, which doesn't make sense, okay, well, not a good friend, or whatever. So, basically, if it's raining, then you know that there are clouds in the sky. Let's go through this. Raining, arrow, clouds in the sky. Okay? If it's raining, that implies that there are clouds in the sky. If it's raining, then there are clouds in the sky. Raining, arrow, clouds in the sky. Clouds in the sky whenever it's raining. Clouds in the sky if it's raining. Okay, so that's a lot of examples of the same idea. Okay, book doesn't think that's enough. Book goes through another 2. Okay, so let's do another 2. This is hard because it's English, not because it's logic. This is just hard English. P is a sufficient. Okay, this is hard English. It's going to take time to get used to this. Sufficient condition for Q. Okay. And one more, let's just write it. Q is a necessary, oh, I don't know how to spell necessary. I really don't know how to spell necessary. Condition for P. Okay, this is hard English, but fine, let's do it. P is a sufficient condition for Q. So let's talk about driving. Driving faster than 60 miles an hour is a sufficient condition, that means you will get it. It's sufficient for you to get a ticket. It's enough for you to get a ticket. Sufficient means enough. You cleaned up your room sufficiently. Okay? Driving 60 miles an hour is a sufficient condition for getting a ticket. Another way of saying it is, getting a ticket is a necessary condition for driving 60 miles an hour. If you drove more than 60 miles an hour, you will get a ticket. That's a way of saying that getting a ticket is a necessary condition for Q. Okay. Q is a necessary for P. Okay, let's do it with raining. If it's raining is a sufficient condition for Q. You want to see if there's clouds in the sky? Well, if it's raining, then there are clouds in the sky. By the way, there could be clouds in the sky without there being rain. So,
the clouds, they take the water from Earth, and then
okay, you have to come here and explain to everybody.
And
okay, but very quickly. Okay, very good. The clouds take the water from the earth and then they put the water back.
That's what they say.
Oh, that's what they say. Okay? Okay, so here's another one. Raining is a sufficient condition for clouds. Clouds in the sky is a necessary condition. You will not have rain unless you have clouds in the sky. Clouds is a necessary condition for rain. Okay, so here's lots of different ways to say it. Okay, let's do it one more example. 2 plus 2 is equal to 4 implies, okay, the world is flat. Okay, now this has nothing to do with this. This is true, this is not true. I'm not interested in what's true, what's not true. I just want to go through the examples. 2 plus 2 arrow, world is flat. 2 plus 2 is equal to 4 implies the world is flat. If 2 plus 2 is equal to 4, then the world is flat. If 2 plus 2 is equal to 4, arrow, the world is flat. The world is flat whenever 2 plus 2 is equal to 4. Again, I'm not interested in if it's true or false. It's absolutely false. This is false, this is true. It's absolutely false. But I want to see the words. The world is flat if 2 plus 2 is equal to 4. 2 plus 2 is equal to 4 is a sufficient condition for the world to be flat. That's not true. The world is not flat. The world is flat is a necessary condition for 2 plus 2 is equal to 4. Very nice. Okay, not interested in that. Okay, let's do something else. I like these examples with the tickets and things like that, and the rain, so I want to go through four ways of talking about these things. Let's go through it. P arrow Q is a proposition. Okay, and now I'm going to make 3 definitions. Definition. Q arrow P is the converse. Okay, so that's a new word, converse. Converse proposition. Okay, let's go through. You know what? Let me just write it out. Not Q arrow, not P is the contrapositive. Okay, that's a new word. Contra, against, positive. You'll see, we'll do it in a second. And finally, not P arrow, not Q is the inverse proposition. Okay, so we have these 3 new things. If you take P arrow Q, we have 3 new things, and I want to go through it each one. Okay, let's do this. P says, if you drive more than 60 miles an hour, you will get a ticket. The converse says, if you got a ticket, then you must have been driving more than 60 miles an hour. Now that's not necessarily true. Okay? You got a ticket because your headlight wasn't working, or you got a ticket because you threw paper out of the window. So that's not necessarily, it's not the same thing. Okay? Let's do it like this. If it's raining, then there are clouds in the sky. That's a true statement. This says, if there are clouds in the sky, then it's raining. That's not true. If you look out the window, you'll see there are clouds in the sky right now, but it's not raining. Okay? So this is a statement. Let's say, if you don't clean your room, I will get angry. I will get angry. I will get angry implies you did not clean your room. No, I can get angry at you for disrupting the class or something like that. Okay, this could be other reasons. Okay, great. Next, contrapositive. Ready? Let's go through this example. Okay, if you drive faster than 60 miles an hour, you will get a ticket. That's P arrow Q. What does this say? If you didn't get a ticket, that means you didn't drive faster than 60 miles an hour. Now that is, these two are related. These two are exactly, they're equal. Let me explain to you what I mean by equal. These two are the same. Let's go through it. If you drive more than 60 miles an hour, you'll get a ticket. It's the same thing as saying, if you didn't get a ticket, you didn't drive more than 60 miles an hour. If you didn't get a ticket, because if you get a ticket, if you drive more than 60 miles an hour, then you'll get a ticket. If you didn't get a ticket, then you didn't drive more than 60 miles an hour. Let's do it in terms of the rain. Ready? If it's raining, there are clouds in the sky. If there are no clouds in the sky, then it's not raining. It's the same thing. Where's the rain coming from? So these two are the same. Okay? Let's talk about cleaning up. Okay? If you don't clean your room, I will get angry. If I didn't get angry, that means you did not clean up your room. That means you cleaned your room. That's very good. Okay, let's go through that again. If you don't clean your room, I will get angry. If I didn't get angry, that means you cleaned your room. Good? Makes sense? Okay, next. Okay, what about the inverse? This says not P arrow, not Q. So let's talk about driving. If you drive faster than 60 miles an hour, then you'll get a ticket. This says if you do not drive more than 50 miles an hour, you will not get a ticket. Now that's not always true. You can get a ticket for littering. You can get a ticket for a broken headlight. So that's not true. But this is the same as this. Okay? Let's just see what this says. This says if you swap the order, P arrow Q, swap the order and put negations on it, then you get something equivalent. Like, watch this. It's Q arrow P, swap the order, and put negations on them, they're equivalent. They're the same thing. Okay? So these are three different statements. For any proposition like this, with an arrow, you get these three other things. And this one is related to this one is related to that one, but they're all very good. Whenever you have an if-then statement, you get these three related statements, and they're very nice. Okay, great. I want to show you something else. Namely, you can write P arrow Q also as like this. Not P or Q. Okay? That's another way of writing it. Just like, okay, so this is an operation, you can do this operation. Let's just see what this says. You ready? If you drive more than 50 miles an hour, you will get a ticket. That means don't drive more than 50 miles an hour or you'll get a ticket. It's the same thing. Okay? Let's do it the other one with raining. If it's raining, then there are clouds in the sky. What is that the same as? It's not raining or there are clouds in the sky. Okay, let's talk about cleaning your room. If you don't clean your room, I will get angry. Clean your room or I will get angry. Okay, they're saying the same thing. Okay, so that's an interesting thing, connecting those two things. Great. So So that was a basic introduction. One second, we have a few more other command operations I wanted to go through. Okay. P exclusive or Q. Just make sure that I have exclusive or. Okay. So the word or in English has two different meanings. Okay, it's very interesting. Almost in every other language, the word or has two meanings. One is called an inclusive or, and one is called exclusive. Okay, okay. So if I say I like ketchup or mustard, so I could like ketchup and I could like mustard, but I also can like both of them. Okay, so I could say today is Sunday or today is a rainy day. Well, it could be Sunday and a rainy day. Okay, both of them could be possible. So that's an example of the inclusive. We allow inclusive. We allow both to happen. Okay, but the word also is exclusive. It means sometimes you have something that could be one is true or the other is true, but it can't be both. For example, today is Tuesday or today is Wednesday. It can't be that today is both Tuesday and Wednesday. Impossible. Okay? You can say I am married to Betty or I'm married to Veronica. You can't be married to both Betty or Veronica. That would be illegal and not very right, especially to Betty. Okay? So you can't say. So it's interesting. You're allowed to say I love ketchup or mustard. I'm not allowed to say I love Betty or Veronica and meaning both of them. Okay, so this is an interesting operation. So this says, let's just talk about the rain. It's raining or, exclusive or, there are clouds in the sky, but not both. Okay, so sometimes it's true. How could it not be both? Well, you could have clouds in the sky and it not rain, that's for sure, but you can't have it that it's raining and not that. Okay, let's do another operation. Double arrow Q. What that says is, if this is true, then this is true. If this is true, then this is true. Let me give you an example. If today is Tuesday and tomorrow is Wednesday. Okay? If this is true, if today is Tuesday, then tomorrow is Wednesday. If tomorrow is Wednesday, then today is Tuesday. So that always works. Okay? So those are these things. So we say this as the words are if and only if, or it's also called biconditional. Okay? Bi, as in bicycle, two ways. Conditional, one way, the other way. So it goes both ways. Okay, great. Okay, now all this is called propositions. 5 more minutes. Just do another semi-topic here. Okay. Okay. So another topic is quantifiers. Okay, and again, these shows up all over. In particular, they're going to show up a lot in chapter 13, and we're going to do that. Okay, so rather than talking about one person, Bill is happy, Miriam is cleaning her room, Baruch is doing what he's supposed to do, what I'm going to do is I'm going to make a function. Okay? And rather than talking about one thing, okay, these things talk about many things. Okay, it'll be more exact when we get later on when we talk about these. Okay, these are called predicates. Predicates. Okay, so h of x stands for x is happy. So I could talk about a lot of different people that are happy or not happy. So I could talk about Bill. Bill is happy. So this stands for Bill is happy. Okay? And then we could talk about Hillary is, okay, this stands for Hillary is happy. Okay? So lots of different things like that. And then we can talk about Monica. Okay, for those of you who don't remember this stuff, and we can talk about Monica is happy. Okay, and then we can also say not H. Bill, which means Bill is not happy. So we can do operations with these things. Okay? Okay. And we can say different things. For example, H. Bill, if Bill is happy, that implies that H. Monica is happy. Okay? By the way, the contrapositive of this is very important. Remember, the contrapositive is the same thing. It says, not H. Monica implies not H. Bill. Okay. If Bill is happy, then Monica's happy. That means if Monica is not happy, it must be that Bill is not happy also. Okay? Okay, great. Now, what are quantifiers? Well, again, this is not a mathematical example. We'll do more mathematical examples in a minute. But what you can do is two things with these things. You can do this. EX, H of X. That's a backwards E. Okay? And that the phrase is that's an existential quantifier. Let's just talk English for a second. Quantifier means what's the quantity? How many? Okay? Existential means there exists. There is one. There is one, there is two, there's three, but there is one. Okay? As opposed to that, for all x, H of X stands for universal quantifier. That means every single one of them. Okay, so let's see what this says. This says there is someone who's happy, and this says everyone's happy. And we're going to see with these two notions we can get a lot of different things. Okay, so let's talk about this. Okay, let's do a more exact example, and we'll see what we mean. Okay, so ready? Let's do E of X stands for, now we're talking about numbers. X is even. Okay. P of X stands for X is a prime. Okay, so now we're talking about, we're not talking about people and who's happy and who's not happy. We're talking about real numbers, and then we have real answers. Okay, so let's go through some of them. For all x, E of X. What does that say? That means every number is even. Is that true? No. Okay, so this is false. This is not a real statement. However, this is a true it is a real, perfectly legitimate statement, but it's not true. There exists an x such that E of X. Is that a true statement? Are there even numbers? Yeah, 2, 4, 6, 8. So this is true. Okay. How about this? For all x, P of X, is every number prime? No. So that's false. Okay. Does there exist a number that's prime?
Yes.
And then that's true. Right. Okay, good. Okay, good. Now, let's do another one. For all x, if P of X, if x is prime and x is greater than 2, this implies it's not E of X. parentheses. Let's see what this says. This is a little bit harder. Look what it says. If for all numbers, if it's prime and it's more than 2, then it's odd. What's not even? Odd. If you're either odd or even. So this says if you're a prime number and you're more than 2, then you're, let's go through the prime numbers. 3, 5, 7, 11, 13, all those are prime numbers. They don't divide by anything, and particularly they don't divide by 2. If you don't divide by 2, then you're not even, you're odd. So this is true. Okay? Okay, how about this? For all x, you got to know prime numbers for this, so implies for all x, if you're prime, that means the next one is not prime. Okay? Makes sense, because if you're prime, you're an odd number. Okay? And the next one is going to be an even number. Okay? 11 is an odd number. The next one is 12, is an even number. So it's not going to be a prime. Okay? This is almost true. Why is it not true? Okay, because there's only one time where this is false. So this is a false statement. This is a true statement, by the way. This is a false statement. When it's the time, if p of 2, 2 is a prime number, and 3 is a prime number. So you have p of 2 is a prime number, and it's p of 3 is a prime number. This is called a counterexample. It's something that's not true, and here's a reason of showing you that it's not true. Okay. Now I want to show you an argument I used to have with my oldest daughter. She used to say to me, I can list the biggest number in the world. And I would say, okay, what's the biggest number in the world? And she would say, a billion, 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 trillion, billion, billion. And I would say, oh yeah? How about a billion, 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 trillion, billion plus 1? And she would get angry at me and she would try another one. Oh, okay, but a trillion to the trillion to the trillion to the trillionth power. And I would say, oh yeah, what about a trillion to the trillion to the trillion power plus 1? And the answer is, she was trying to win an unwinnable game, because she was thinking that the numbers, she was trying to say, I'm going to list off the biggest number possible, but there's always another big number. What? The next one. Okay? So the way to say that there's an infinite set of numbers is as follows. For all x, for all x, give me any number whatsoever, there exists a y such that y is bigger than x. Okay? Give me any number whatsoever, for all x, there is a y such that y is bigger than x. Always is. Okay? 52, 57. Okay? 128, 145. There's always a bigger number. Okay? Now, let's talk about something else. How about this? For all x, if p of x implies there exists a y such that p of y. Let's see what this says. This says any number that you find a prime, there's going to be another number, and it's also going to be a prime. Oh, hold on. Didn't do that right. Y more than x, p of y. Look what it says. For all x, p of x, if x is a prime, that means there's another number, y is greater than x, and p of y. There's another number bigger. So the point of this is, there's an infinite number of primes. This says infinite numbers. There are infinite numbers. This says infinite primes. Okay, great. Now I want to teach you a new definition. Okay, I'm just doing this to give you lots of examples with these quantifiers. Okay, twin primes. Okay, so let's go through some examples. 11 is a prime. I'm sorry, let's start earlier. 5 is a prime. 7 is a prime. 11 is a prime. 13 is a prime. 14, 15, 16, 17. 17 is a prime. 19 is a prime. 19 is a prime. No. Give me another one. 21 is not. 23 is a prime, but it's not. 25 is not a prime. 26, 27, 41 and 43 are both primes. 29 and 31 are both primes. These are called twin primes. They're prime numbers and then one after each other. Okay? And the question is as follows. Okay, so these are called twin primes. So let's just do it. P of x is a prime, and P of x plus 2 is a prime. Okay, one number and the other one. Okay. The question is as follows. We'll move. Let's do it carefully. For all x, let's just see what this is. P of x and P of x plus 2 implies there exists a y such that y is greater than x and P of y and P of y plus 2. What does this say? This says if x and x plus 2 are primes, that means these are twin primes, x and x plus 2 are twin primes, then there exists a y, a number that's larger than x, such that y and y plus 2 are also twin primes. What this says is that there's an infinite number of twin primes. Okay? There's an infinite number of twin primes. Now we ask a basic question. Is this statement true or false? Is it true? We know that there's an infinite number of primes. We know that for every prime number, there's another number two points away. Is there an infinite number of twin primes? Is this statement true or false? Answer, we have no idea. We have no idea. We know what primes are. We can talk about primes. We can prove theorems about primes, but we have no idea. This is a very old math problem that nobody has the solution to. Anyways, so that's interesting. So that was a first introduction to logic. We're going to do another, section 2.1 is more logic, where we get down to truth tables, which are a fundamental part of logic. Okay? Got to do the homework problems, so we're going to do the homework problems here, but first do the homework problems on your own. Take care.